Hello everybody, in this video we will discuss acidity of alpha hydrogens. So let's discuss what is an alpha hydrogens. So when we say alpha hydrogen, we are talking about alpha to the carbonyl group. So we have carbonyl groups here, and the carbon atom that is right next to that carbonyl group is called alpha carbon atoms, right? So that's the functional group here, carbonyl, and the carbon atom right next to the functional group is gonna be our alpha carbon atom. So in this case, our alphas are gonna be all the red carbon atoms right here. So these are all ours alpha carbon atoms. Now the hydrogen attached to those carbon atoms are going to be our alpha hydrogen. So this is gonna be your alpha hydrogens. So alpha hydrogens, and this is gonna be your alpha hydrogens. All right, so the nomenclature systems in carbonyl containing compounds. So let's say you have something like this. So the carbon atom that is right next to the carbonyl group is called alpha. So in this case, this one is gonna call as alpha carbon atoms. Next one is gonna be beta. Obviously next one is gonna be gamma. So if we have hydrogens there, feel free to add hydrogens there. So those are gonna be corresponding hydrogens, alpha, beta, gamma, and next one delta, and so on. So in this case, the hydrogen attached to the alpha carbon atoms are gonna be your alpha hydrogens. Okay, so it turns out the alpha hydrogen is acidic. So alpha hydrogen is acidic. So if you provide a strong base, so let's say I'm gonna use one of these as an examples. So let's say if I have a strong base, so let's say I will write down here. So if I use a very strong base, such as let's say B minus is a strong base, is a very strong base. What would happen is this B minus can actually abstract this particular hydrogen. So again, all of these are alpha hydrogens, so it will abstract one of these threes, right? So if it does, what would happen to this electron here? So these electrons, so once the proton is gone, so let's say this hydrogen is gone. So what happens? These two electrons get stuck with the carbon atoms, okay? So I'm gonna bring them back here. So I will draw the reactions here. Okay, so here CH, H, CO, H, H. So once our B minus abstracted a hydrogens, then the carbon atoms will get the electron. So if the carbon atom gets the electron, how does it's gonna look like? It's gonna look CH, H, H. So now carbon atom has extra electrons, so as a result it's going to have a negative charge. So people always ask me, where does the extra electron comes from? So if you noticed, I'm going to explain here. So if you noticed, how did this bond actually being created? So this bond is actually being created by covalent bond, right? So where carbon's gonna provide one electrons and hydrogen's gonna provide one electrons, and all of these bonds are formed by that method, right? So all the carbons provided one electron. So you see how many electron carbon has? 4 electrons. And then all the hydrogen provide to this beautiful partnerships where they created the covalent bond. Now it turns out when you get rid of your hydrogens, this hydrogens left an extra electron with the carbon atom. So now you have a situations where one electron was from one extra electron. So one extra electron, this blue electron came from hydrogen. So as a result, carbon has negative charge. Okay, so that's how we can explain. Okay, I will bring them back. I will redraw the bond so that it will look prettier. Okay, so we got our C minus right there. So what happened is this negative charge can be delocalized across the CO bond. So this negative charge can be delocalized. So negative charge on carbon atoms can be delocalized across the CO pi bonds, right? So we got CO pi bonds. So what would happen is this here can, these two electrons, so these two electrons, okay, I should draw this other way. So there is a negative charge here. There is a negative charge. So these two electrons can be delocalized with the CO pi bond. So we can create a resonance contributing structure, so where it would look something like this. So we got CHH double bond CO minus. So you see the negative charge move from carbon atom to all the way to oxygen atoms. So I can show the all the electrons. So now oxygen has negative charge, 6 electrons, n plus 2 8. All right, so because we created a resonance structure, so conjugate base is stable. So this is the conjugate base, right? So if this is your acidic proton, if the hydrogen is gone, then what's left over is your conjugate base. So this is the conjugate base. So this is the resonance structure. So two resonance structures for the conjugate base. Okay, so again, so we can deprotonate this based on this. So it is acidic enough. So usually the pKa of these two hydrogens, so pKa of these two hydrogens are around 16 to 20. So pKa of these alpha hydrogens is around 16 to 20. Again, it's just a round number. Okay, don't be precise. It depends on the what's attached to. Maybe chlorine is attached, then the pKa will increase and so on. However, when you have ester, so we have an ester group here. So here it's simple aldehyde and ketone, but whenever it's connected to an ester, its pKa is gonna be way higher. So the number is gonna be closer to 25. So pKa of an alpha hydrogen connected to an ester is going to be lots higher, so which means it's going to be less acidic. So the pKa, this alpha hydrogen is going to be less acidic. Okay, let's stop this video here. So well, let me explain a few things. So because we created a C negative charge here, so this is called enolate ions. So this is the resonance structure of our enolate ions. Enolate. So the name enolate derived from this structure because this is the structure of enol, which I will discuss in the next video. And once the hydrogen is gone, it's enolate ions. So this is the resonance structure of enolate ions. And you can see here we have a C negative charge. So once you have a C negative charge, we can use this C negative as a nucleophile to attack anything we want. And this is going to be a basis of your reaction. So if you get the idea of deprotonation of alpha hydrogen, you can do many of these reactions where C negative would serve as a nucleophile and go on attack anything you want. All right, so let's stop here.